So it's been a few months, and it's time for an update on the latest server in my fleet, the Inspur DGX V100. Over the last couple weeks, I've been running some tests to see how it performs when running AI models. While the ultimate goal is to open up this server to my Patreon, allowing users to access various models in the cloud, I need to see how everything performs first, along with figuring out how to grant access to the server once it's up and running. Today though, I wanted to go over some of my early benchmarks, talk about why a massive 8 GPU server like this, despite its age, might still be relevant today, and go over some benchmarks against some top consumer GPUs. And I'm sure all of the AI bros will tell me that I did everything in this video wrong. So, what do you say we learn something together? Welcome back to Craft Computing, everyone. As always, I'm Mikey. Before we get started, once again, a huge thanks to Unix Surplus for sending over the Inspur DGX V100 for this little experiment. Links on where to buy the same server will be down in the video description if you're interested in picking this one up for yourself. A quick recap, the system is running 8 Nvidia Tesla V100 GPUs in the SXM2 form factor. Each card contains 5,120 CUDA cores based on Nvidia's Volta architecture, a design that never really made its way down to consumers, sitting between their Pascal and Turing lineups. Each card also has 32 GB of HBM2 memory on board with a 4096-bit bus. In total, we're looking at roughly 900 GB per second in memory bandwidth per card, and a total of 256 GB of video memory in the server. In the world of modern AI processors, that might not sound like much though, what with the Nvidia B300 boasting 288 GB per GPU and up to 2.3 TB per system. But at just over $6,000, the Inspur DGX V100 might still be one of the most affordable ways to run some of the latest high-demand LLMs. But even $6,000 is a lot of money, especially if you're simply looking at evaluating whether or not an AI workflow might be beneficial to you or your business. Instead of investing in pricey hardware, you should take a look at the sponsor of today's video, Verda, formerly DataCrunch. If you've been struggling to spin up AI models on your current hardware, or are hesitant to invest tens of thousands of dollars, Verda might be for you. They offer instant access to high-performance Nvidia GPUs, optimized clusters for training large AI models, and serverless inference with auto-scaling, all without waiting days for provisioning. They offer GPU solutions to fit any budget, from the V100s like I have here, all the way up to Nvidia's latest B300 GPUs, ready to be put to use in your most demanding workloads. What's more, Verda data centers run entirely on renewable energy, so your AI workloads don't just run fast, they also run green. Plus, with all Verda's servers residing in the EU, they're protected under GDPR and some of the world's strictest data privacy laws. You get secure ingress and egress of all of your data with no hidden compliance headaches. Whether you're ready to move your AI workflows to the cloud, or just need to evaluate which solution is right for you, Verda is the cloud provider that is fast, affordable, private, and sustainable. Check out what Verda has to offer by going to verda.com or clicking the link down in the video description. Plus, if you use coupon code CraftComputingV100, you'll get $25 off at checkout. Again, that's verda.com, and thanks again to Verda for sponsoring today's episode. Starting off, what exactly are we testing here today? Obviously, the DGX V100 was built for machine learning and AI workloads, but it's also pushing 8 years old. As I mentioned, while the sheer amount of memory still dwarfs modern consumer GPUs, with up to 256 GB combined, it barely moves the needle against recent data center chips. It's no surprise that hyperscalers are starting to move on from V100s, but for smaller organizations or even extreme home labbers like myself, it's still among the cheapest ways to get that much video memory into a single system. Now, on top of the 8 Tesla V100 cards, the Inspur DGX is also loaded when it comes to traditional compute, with a pair of Intel Cascade Lake Xeon 8260 CPUs, each of them with 24 cores and 48 threads, giving us a total of 96 threads to work with. We've also got 512 GB of DDR4 ECC memory, meaning even if AI models can't fit entirely into our massive VRAM cache on the V100s, we still in theory have plenty to offload for larger models. I say in theory because my goal here is to run AI models entirely in VRAM, as that's how we'll see max performance. Plus, as I'm testing consumer GPUs on a different system entirely, I don't want to conflate my results by running outside of the GPUs themselves. In the first video with this server, I installed a full set of 8 1.92 terabyte Patriot Burst SSDs, assuming that with a 2-drive failover in a RAID Z2, these inexpensive SSDs would work just fine. Well, a week into testing and one of those drives failed. Another 3 days later, and I had a second drive fail. Luckily, Unix Surplus again had my back and shipped out 8 Samsung 1.92 terabyte Enterprise SSDs to get us back up and running. For testing the V100, I've got Proxmox installed, which will allow me to create VMs and be able to pass through V100s in whatever quantity that I need. This will allow me to quickly test one GPU, 2, or even all 8 at the same time without complicated configurations or reinstalling the OS onto bare metal. Keep in mind, the server is up at 01's YOLO Colo, so everything that I'm doing with the server has to be done remotely. To get things started, I ran MLPerf, a standardized benchmark suite developed by ML Commons for testing AI and machine learning performance, regardless of the platform. And while this test is designed to run on any hardware that you have, whether CPU or GPU, it also seems to benchmark only a single GPU, rather than being able to scale to multiple cards. As such, we're going to be able to get numbers for a single V100, but not see how well they scale with multiple cards running a single model. But the numbers are still interesting, especially considering that the Tesla V100 is 8 years old at this point. In Llama 3.1, we see an average time to first token at 0.33 seconds and 84.6 tokens per second. Comparing those results to the current top-end consumer card in the RTX 5090, it's no surprise to see the 5090 way out in front, running a full 2.5 times faster with 211 tokens per second. But that's also not the whole story. While the 5090 was faster, it also peaked at 475 watts during testing. Meanwhile, a solo V100 peaked at just 175 watts, making it actually slightly more efficient per token than the 5090 was. Moving on, the RTX 5080 is almost exactly half the performance of a 5090 in gaming, but it managed to come in well above the halfway mark at 143 tokens per second, while also well outpacing the V100 for both speed and efficiency. Now, one thing that I wanted to figure out was what modern GPU is the V100 equivalent to when it comes to AI testing. So I did quite a few more tests and finally dropped in the RTX 4070 Super and got a result of 88.6 tokens per second. And it looks like we might have a winner. The V100 trades blows with the RTX 4070 Super, staying within about 5% of it in every metric that I tested. But there's also one big caveat in the 4070 Super, as it only has 12 gigabytes of VRAM compared to 32 gigabytes in the V100. Obviously, the 4070 Super is less expensive, but you're also going to be hard-pressed to get 8 of them into a single server, let alone into a 2U space like the Inspur DGX system that we have here. With the stock air cooler, you could possibly fit 4 of these cards into a 4U server, or upwards of 7 of these GPUs if you went with a full custom water-cooled solution and cut them down to a single slot each. But that's still less than half as dense when it comes to GPU compute per U, and barely 1/3 the VRAM capacity of the V100s. Looking at the 5-4 reasoning benchmark, the results are nearly identical. The V100 comes in with 59.7 tokens per second, with the 5090 clocking 138, or roughly 2.3 times faster. The 5080 also comes in almost exactly between the two again. In this test though, the V100 comes in well ahead of the 4070 Super, at roughly 15% faster. As I'm sure a lot of you will be quick to point out though, a 14 billion parameter model isn't exactly stressing the VRAM on any of these GPUs. Unfortunately, that was the largest model available in MLPerf, but it still gave us a good idea of what kind of speed we'll be looking at when it comes to single GPU instances. For smaller models, there's no reason I couldn't run 8 VMs in the DGX V100 with 8 of these different models installed. But what about a larger model that requires a ton of VRAM? The easiest way I know of to run large models on your own hardware is through a program called LM Studio. It allows for downloading massive LLMs and running them offline locally on your own system. There are advantages and disadvantages of using LM Studio. On the upside, it's multi-platform, so you can run the same models whether you have Windows, Linux, or even Mac OS. And it works with just about every hardware type as well, whether you have Nvidia, AMD, Intel, or even Apple. You give it a GPU or CPU with enough memory, and it'll run the model for you. The downside, though, is it is 100% local to your PC and your local desktop GUI. There's no web UI to access the models remotely, So you can run it as a local user on your desktop, but not from another PC. So it's great for testing which models can run on your hardware, but not great for me and wanting to share access to these models to multiple people. The models we tested in MLPerf were 8 billion and 14 billion respectively, and those can both pretty easily run inside of a 12GB GPU, with little to no spillover into system memory. So what happens when we jump to a slightly more demanding model, like Meta's Llama 3.3 with 70 billion parameters? A 70 billion parameter model, according to this very AI, can require up to 280 gigabytes of memory to store model weights. However, in my testing, that number was closer to 48 gigabytes, running 4 Tesla V100s, with each GPU allocating roughly 12 gigabytes of VRAM to store the model. And the system did register around 52 gigabytes of system memory as in use while the model was loaded, but LM Studio was only using around 3.5 of that. Now, I fully admit I'm not throwing the most intense prompts at this model, but 4 GPUs seems to be more than enough for it to run quite well. On average, we're seeing around 14.5 tokens per second. The first question asked when the model was loaded did take around 6 seconds to generate the first token. After that, subsequent questions were much faster at around 1/3 of a second. When I throw all 8 GPUs at the model, those numbers didn't change at all, still sitting right around 14.5 tokens per second, with a TTFT of around 0.3. This lines up with some of the advice I've given before around running AI models. Most of the time, if you can fit a model in memory, it'll run on whatever GPU you give it, and more compute doesn't necessarily mean faster or better results. In the case of Llama 3.3, we're easily able to hold the entire model in GPU memory, and the added compute doesn't help it process any faster. In fact, even dropping down to just 2 V100s shows little to no impact in performance, seeing even slightly better results of 15.5 tokens per second, and a similar TTFT of 0.25. Given we're still seeing 48 gigabytes of VRAM utilization, I would still need at least 2 V100s to run this model. But that also means I could easily run 4 70 billion AI parameter models on this server at essentially full speed. But what if we wanted to go even larger? Jumping up to a 120 billion parameter model doesn't necessarily mean we'll be giving up performance. Llama 3.3 is what's known as a fully dense model, meaning that every parameter of the model is used for every calculation. We can actually move to a larger model, say OpenAI's GPT-OSS with 120 billion parameters, and actually see improved performance despite its much larger size. GPT-OSS is known as a dense model with no MOE, or mixture of exports. Essentially, it's a more efficient transformer model and can lead to around 70% more flops per token despite the larger database. The larger dataset does mean significantly increased memory requirements, with around 60 gigabytes utilized by the GPUs. However, it should be noted that GPT-OSS refused to load when I had just 2 of my V100 32GB cards installed. I had to move to 4 GPUs for the model to load without errors, and even then, I ran into an issue when it came to inference. See, each token generated by an LLM still takes up space when interacting, and those tokens need to be queried if your conversation continues beyond 1 or 2 simple prompts. The default context size in LM Studio is 4096 tokens, which fills up rather quickly on such a large model. I didn't even make it through my second question around hardware requirements before the context overflowed and the model simply stopped responding. Every response from an LLM generates tokens, and the longer your conversation is, the more tokens need to be generated and stored. And the larger your model, the more tokens are required to search the massive parameter database and generate responses. So it's not just model size that you need to take into account, it's also the size of the responses that you generate. Each model that you install will have a max context size and needs to be configured to meet your needs. Each model has its own practical, theoretical, and breaking point limits when it comes to context length as well. Tokens require space. As an FP16 workload, one token is around 256 kilobytes in size. That means 100,000 tokens is 25 gigabytes worth of context, and that needs to be stored on top of your model memory requirements. In theory, GPT-OSS with 120 billion parameters can support up to around 130,000 tokens, but anything beyond around 32,000 can start to cause stability, or worse, hallucination issues. But all that said, I was able to get GPT-OSS 120B up and running on 4 V100s, and saw some rather impressive performance, upwards of 60 tokens per second, which is actually right in line with what the AI model told me I should be seeing on this exact hardware. So running large models is definitely still very possible on this hardware, and likely much more affordable than buying 4 RTX 5090s or a pair of RTX 6000 Pro Blackwell GPUs to make it happen. So some pretty interesting results, and definitely encouraging knowing that $6,000 can still run some pretty impressive models, even given the age of the hardware here. But I did run into a couple funny scenarios with these offline models. One of the main benefits of LM Studio is the fact that the models run entirely offline and cannot access the internet. This means your data stays private, and nothing you send into it will leave your server. However, that also means that it won't seek out new data or confirm any of its output by searching the internet. Let's take me as an example. I'm Jeff with Craft Computing. I say it at the beginning of every video I've ever published. But I'm also not the most popular channel in the world, and outside of my niche of home labbers and server enthusiasts, you're unlikely to actually know who I am, which makes me the perfect test candidate for seeing whether or not an AI is bullshitting you with its output. GPT's OSS model is current up to September 2023, which means it should, in theory, have 7+ years of my channel to look back on, if that data is in fact in its database. Asking, are you familiar with the YouTube channel Craft Computing, gets an enthusiastic yes. Craft Computing is run by Mike, aka Mikey, a former software engineer turned full-time tech educator. Last time I checked, I'm Jeff. In fact, I've always been Jeff. So it got that wrong, but what else did it miss on? According to AI, my channel was founded in 2020 with simple how-to videos around Raspberry Pis and Arduinos. I have a Discord community of around 12,000 people. I host monthly hackathon events along with a Challenge Corner series where viewers submit project ideas and I build them live on stream. Obviously, none of that is accurate, so I decided to challenge the response and ask it to cite sources just for my name. I'm sorry about that mistake. The channel's primary presenter isn't named Mike. The correct information, with publicly available sources, the Craft Computing YouTube channel is run by James Miller, who appears in every video introducing himself as James or Jay. And he has a trademark intro, starting every video by saying, "Hey everyone, I'm James, and welcome to Craft Computing." That's closer, I guess, but the problem is 80% of the way there only gets us to James, not to Jeff. But things actually get worse from there, because it's not just the fact that AI made up everything about Craft Computing. When challenged, it cited sources directly to my relevant social media pages, including my YouTube About page. It made up a Wayback Machine snapshot to establish my first video published. It made up Social Blade listings for my channel size and origin, an inaccurate Discord link, and a link to my Patreon where it again claims that the creator's name is James Miller. But the links that it provided did land on my social media pages. So I wanted to go just a little bit deeper, asking what some of my more popular videos were. And I got a list of 10 videos that not only have I never produced, but searching for these titles on YouTube yielded 0 results. I don't know if I'm more offended that AI actually doesn't know who I am, or that the viewership numbers it's claiming are tenfold what my channel actually does. I can take solace in the fact, though, that even though AI thinks I produce content around Raspberry Pis, at least this time it didn't confuse me with Jeff Geerling. That only happened when I was writing this script inside of Google Drive. I decided to repeat this test a couple different times, in a new chat window with fresh context every single time. And each time, AI made up some new bullshit about my channel, who I was, and what videos that I've published. Everything from retro computing and Commodore 64s, to a software developer, to Raspberry Pis and Arduinos, but never home lab, open source enthusiast, gaming, beer reviewing, or anything that I actually do. But there was one anomaly that was repeatable that I can't fully explain. Whenever I prompted AI to tell me how up-to-date its training data was, it always responded with September 2023. When I started a conversation with that specific question, and then asked about Craft Computing, I received an honest answer of, "I don't know." And that right there is the inherent problem with generalized AI and LLMs. AI has been trained to give human-readable responses to questions, not to be able to fact-check or to reason, even though this model is technically a reasoning model and should be able to fact-check itself. I'm sure you've seen the same thing on most online models as well, where when questioned about the factuality of a statement, AI will instantly simply agree with you, rather than its own dataset or even looking up sources to confirm. As long as the data is approximating what a user wants to see, the LLM has achieved its goal. Now that's all to say that AI still has a ton of use cases, and this video is not necessarily designed to side with one side or the other for any viewpoint. LLMs are something that exists, and people might want to run them on their own hardware. And I wanted to demo both the models running as well as demonstrate pros and cons of running these models. It's up to you, the user, to decide what to do with it and how to use it. I'm not necessarily anti-AI, as there are tons of areas that benefit from its use, from cancer research and diagnostic imaging, real-time machine vision, logistics and safety in industry. In fact, I recently did a video with Supermicro talking about some such use cases. And while text LLMs also have their use cases, in my opinion, they shouldn't be used for research or fact-checking. The output they're designed to give is trained on, yes, I have that answer to that question, rather than, let me find the answer to that question. Using an LLM for non-research tasks, though, can be extremely powerful, from checking the tone of an email that you want to send, to helping reword or summarize what you've been reading. I don't mind the use of LLMs as writing aids, but the facts and research should still be entirely from humans. All that being said, while this video is 100% about LLMs, not a single word in this script was written by or assisted by an AI. Nope, you can blame me, James Miller, for 100% of the content here. Back to the hardware itself. I'm actually really impressed with how well the Inspur DGX V100 performed overall. While it is absolutely out of reach of most users, for small businesses or the 1% of home lab enthusiasts out there who are wanting to experiment with AI models, it's still likely one of the most affordable self-hosted options out there. With 256 gigabytes of VRAM and 256 gigabytes of DDR4 ECC, with the ability to load it up to 1.5 terabytes, the possibilities are pretty high with what models you can run on a system like this. Again, huge shout out to Unix for sending out the Inspur DGX V100 system for this project. Links on where to pick one up for yourself, as well as to see all the rest of the hardware they have in stock, will be available down in the video description. If you have any other AI use cases you'd like to see me run on this server, let me know down in the comments below. I'm also looking for recommendations for granting access to the system to my Patreon backers, either through authenticated web access or maybe even a Discord bot integration. So if you have a suggestion for that, feel free to drop a comment down below. Speaking of the Discord, the only way to get access to it is by joining the Patreon. Rather than 12,000 random internet trolls like AI claimed earlier, we have about 800 active monthly users in a very close-knit community, with the Patreon serving as a moat to keep the trolls at bay. If you want to chat directly with me, join the Patreon by following the link down in the video description. And that's going to do it for me in this one. Thank you all so much for watching, and as always, I'm Jeff, and I'll see you in the next video. Cheers, guys. Beer for today is from Deschutes Brewing. It is a non-alcoholic, fresh squeezed IPA, clocking in at 0.5% or less. Always love Deschutes fresh squeezed, and kind of curious to see how the non-alcoholic version stacks up. Looks like a beer so far. So I will say, for a non-alcoholic IPA, this is pretty solid. But as I'm drinking this, I can't help but miss Athletic Brewing just a little bit. I'm a huge fan of Athletic Brewing. They make a series of dynamite non-alcoholic beers. Hazies, IPAs, brown ales, golden ales. All of them are pretty fantastic. This one from Deschutes, their fresh hop, it's good, but it's definitely a step down from the standard fresh hop IPA. And unlike the Athletic brews, there's a little bit of a tell that this one is non-alcoholic. Anyone who's had one of the cheaper non-alcoholic beers, I think O'Doul's made some for a while, there's this like rice-like flavor that sits in the back of your throat and just kind of accumulates. It's not terrible with this beer, but it is present. And it definitely takes away from every bit of flavor that this beer does have. It's really good right up front. It's got a little bit of that strata galaxy hop kind of bite to the front of it, which is really pleasant. But then as soon as I swallow, the only thing I'm left with is that slightly burnt rice husk kind of flavor in the back. And it really takes away from the experience overall. Not bad, but definitely could be better.